Homework. We are on particle kinematics. Number 9. Okay, so we have a path that this particle follows, and if you want to visualize it, it looks like this, and in the direction of decreasing x, so it's going this way along the path. And the speed is given. So what's the velocity vector as a function of x? So this isn't asking for the acceleration, so the really tedious part is left out of this. This is more the kind of question that I would ask on a test, you know. And then separately, I would probably ask a question where I give you velocity as a function of x, y, or z, but it's a simpler derivative to do, you know. Okay, so the parameterization looks like this, x and y, which is x squared. And so our first thing we want to do is find a vector that's tangent to the path in the direction of motion. So that red vector is what we want first. That it won't be a unit vector to start with. So u is plus or minus d dx of x squared. So that's 1, 2x, and it's in the direction of decreasing x, so we want the negative. Any questions about that? And now we want the unit vector in that direction. So the magnitude is, you know, you could write this as -1, -2x. So the magnitude of this vector is -1 squared plus -2x squared, 4x squared, all square root. And so the unit vector then is this magnitude, well, this vector divided by this magnitude. So I'll write that as -1 over 1 plus 4x squared square root, -2x over 1 plus 4x squared square root. And now the last step is the velocity vector is the speed times the unit vector in that direction. The speed is 2x. So this is -2x over 1 plus 4x squared square root. And then -4x squared over 1 plus 4x squared square root. So that's the velocity vector as a function of x. Any questions about that one? Any other homework questions you want to see? Okay. So I said that there are 4 topics in particle kinematics. with a non-rotating coordinate system. The first one is just doing differential equations and derivatives and stuff to go back and forth between the acceleration and the velocity and the position. That's when you know stuff as a function of time. Next, there's the chain rule. That's stuff like this problem here where you know the velocity, or you have a way to find the velocity as a function of a position variable. And then the last two are relative motion and circular and spherical motion. And we're going to see that in this class, we're going to use 3 and 4 together like all the time. Okay, so we're getting into, we've done this one, we've done this one. So now we're getting into relative motion. And maybe the most important use of relative motion in this class is, so I don't know, I'm going to say that's the most important use. We'll do this a lot. And this is for using coordinate systems with accelerating origins. Okay, so in Physics 1, when you first talked about Newton's second law, you were told that it holds in inertial coordinate systems. And there are two requirements for a coordinate system to be inertial. It can't be rotating, so the axis orientations can't be changing in time, and the origin can't be accelerating, okay? Later on, we're going to learn how to deal with coordinate systems that are rotating. But this is how we are going to deal with origins that are accelerating. So this is kind of like dealing with one half of the problems of non-inertial coordinate systems. Okay, so let me tell you some things to remember as we do this. That's too many embers. Remember. Ooh, embers. Remember. So the first one is this coordinate system thing always can feel kind of abstract. Like, what am I talking about when the coordinate system axes are rotating or whatever? But physically, just always think of a coordinate system as a video camera that's recording motion, okay? And it's set up in such a way that it can record distances, and you can record speeds and directions and everything. So just think of a video camera. No, think of a coordinate system as a video camera. Okay, so Imagine that you have a video camera at Valley Fair. Does Valley Fair have like a free fall ride? They must. Everyone does, right? So imagine that the video camera is looking at you at Valley Fair in Shakopee on Memorial Day. It's only $49 a person per day. And this camera is watching you do this free fall thing. And this camera is mounted to the ground, okay? And so it's looking at you, you turn it on, the thing drops, this camera measures your acceleration downwards at 9.81 meters per second squared, okay? Then does that acceleration match with Newton's second law? Yes, because if you draw a free body diagram, the only force on you is gravity while you're in free fall, okay? And so that set up Newton's second law and everything works perfectly, okay? But now think about this, like, so now there's a camera, but it's dropped at the same instant that you're dropped, okay? Now what does the camera measure, okay? Now the camera just measures you screaming, but in the camera's view, you're not going anywhere. You know what I mean? And so that camera now has this information in it that says your acceleration is 0. Well, your free body diagram still has the weight force on you. So what happens when you put it into Newton's second law? It looks like Newton's second law doesn't work, you know? So that's the idea of a non-inertial coordinate system and why the laws of physics don't work in a non-inertial coordinate system. And this is how we're going to correct for that, okay? So this is kind of what I said above, but there are two ways a coordinate system can be non-inertial. The first one is an accelerating origin. The second one is rotating axes, or let's just say a rotating coordinate system. Relative motion is how we account for this one. So once we've talked about this, you would know how to correct your data from that camera that the camera, according to the camera, you're not moving, but we'll know how to correct for that. If the camera's spinning, we still don't know how to deal with that, but we'll do that later. And then the third thing is in this class, so this isn't always true generally, but in this class, any two coordinate systems are instantaneously aligned. So when I go through relative motion, we're going to imagine a coordinate system like this and a coordinate system like this, and they can be moving differently, but their orientations are the same. Okay? You know what I mean? And later when we're talking about rotating coordinate systems, well, we'll have one coordinate system that's orientation is changing in time, but at the instant that we're thinking of, they're always going to be instantaneously, boom, this is where we're considering it, and then it moves past, okay? So we're not going to, so this class, it's not like it's super hard, but in this class, we're not going to deal with a case where those have different alignments. Okay, so relative motion, in a way, it's kind of more a notation than anything else. Let's think about an object. So this is relative motion for positions. And let's say that there's a coordinate system A and an aligned coordinate system B. And then a point P. And each one of these is a video camera that's measuring the location of P. Okay, so according to coordinate system A, this is the position vector. According to coordinate system B, this is the position vector. Okay, well, we're used to just talking about a position vector, but now since we're doing them in two separate coordinate systems, we need kind of a new location, a new notation for this. Okay, so here's the notation we're going to use, and you have to get used to this. This is going to come up a lot. We're going to call this red vector is the position of, anyone remember this from Physics 1? What that notation is for relative motion? Anybody do relative motion in Physics 1? Oh, if you didn't do it, it's hard to remember it. Yeah.
Well, I did, but I don't remember.
Yeah. Okay, so it's the position of the point P relative to A. So there's the notation. Okay. Position of P relative to A.
Can't just do P sub A.
Let's do this. Forget about the P. P stands for position. Let's call this C. Okay, so this is the position vector of C relative to A. And this is the position vector of C relative to B. Okay. And now there's a third relationship. This blue one is the position of B relative to A. Okay. Well, notice that now that I've drawn all these vectors, this is just a vector addition thing. That vector PCA is the sum of those other two, by the way vector addition works. Okay, and so the position of C relative to A is equal to, I'm going to write it as the position of C relative to B plus the position of B relative to A. And you could always draw out that triangle of vectors to come up with this, but there's an easier way to do it here. So this is like a memory device. Think of this as fraction multiplication. If you look at just those subscripts, this says C over A is equal to C over B times B over A. Okay, so whenever you're doing relative motion problems, if your subscripts satisfy this multiplication, then you know it's you know you have the order right.
It's not like derivative.
What?
This look like the derivative, like when.
Oh, yeah. Yeah, like chain rule, yeah. Uh, and so now that we have this, now to come up with the relative motion equations for velocity and acceleration, all we have to do is take time derivatives of everything. And so the velocity of c relative to a is equal to the velocity of c relative to b plus the velocity of b relative to a. And the memory device has to hold for this too. And then for accelerations, the acceleration of c relative to a is equal to the acceleration of c relative to b plus the acceleration of b relative to a. And this memory device has to hold for that one too. One thing to notice as we go through these, so this is something that's always true. Sometimes it comes in handy. Is no matter what your subscripts are, this time I'm gonna call it M and N just so they're representing something random. The position of M relative to coordinate system N is the negative of the vector position of N relative to M. So let's make sense out of that. If these two, like look at coordinate systems A and B, for example, okay? The blue vector is where A says B is. But if you also think of B as a video camera, then the exact opposite direction, just put the head on the opposite vector, where you just put the head on the other side of this vector, is the position of A according to B. Okay, like that Spider-Man meme. I know you kids like memes. Okay, and this is true for velocity and acceleration too. So if you ever, this is helpful if you ever put your equation together and then you're like, shoot, I have one of my subscripts switched so they don't all fit together. Just use this negative rule. So the velocity of M relative to N is negative velocity of N relative to M. And then same with acceleration. Acceleration of M relative to N is equal to negative acceleration of N relative to M. Okay, so let's see, I guess, a couple of examples of how this works. So let's say that an elevator starts to move. And a passenger drops their keys. According to a camera on the elevator, a camera that's mounted to the elevator, the observed acceleration is 11.5 meters per second squared down. Okay, so that's just what the camera sees. And the question is, what's the acceleration of the elevator? Okay, well, we know two things. We know that the acceleration of the keys relative to the elevator are 0, negative 11.5, if we have like our sort of usual coordinate system. And we know that for something in free fall, according to the ground coordinate system, the acceleration of the keys relative to the ground are 0, negative 9.81. So just for your notes, this is the acceleration of the keys relative to the elevator. This one is the acceleration of the keys relative to the ground. And what we want is the acceleration of the elevator relative to the ground. Okay. Well, you could manipulate these equations. Like there's kind of two ways to do it. You can find a way that these fit together in this form and solve for it, or you could just put it like, the thing you want is equal to plus or minus acceleration of the keys relative to the elevator, one thing you know, plus or minus the acceleration of the keys relative to the ground, the other thing you know. And now we just switch it to the negative if we want those subscripts switched. So notice that to make the fraction multiplication work, we would want the elevator relative to the keys here, then it would work. So I'm going to take the negative of this. So this is negative acceleration of keys relative to elevator plus the acceleration of the keys relative to the ground. And the reason this works is because this is now the acceleration of the elevator relative to the keys. And so the acceleration of the elevator relative to the ground is equal to negative 0, negative 11.5 plus 0, negative 9.81. And so you get, I don't have the answer to that. Anyone have a calculator? What's 11.5 minus 9.81?
Negative 21.
This negative cancels that negative, so it's
Oh, my bad.
11.5 minus 9.81. 1 point, yeah, 1 point something.
69.
69? whoops. And this is a vector. So from that calculation, we figured out that the elevator is accelerating up at 1.69. Any questions about that? Hey, that clock is right. Yay. Okay, let's do another one. So let's say that a car, is in an accident, and a camera mounted to the car, like inside the cab of the car, sees, a coffee cup falls when this happens, and it sees the coffee cup accelerate at, well, if you're sitting in a car and you suddenly stop and your coffee cup is just sitting on the console, what does it look like to you the coffee cup does? Where does it look like it goes? Forward. So this is going to, let's say that this is an acceleration of, let's say, 15, negative 9.81. What's the acceleration of the car? Okay, I'm going to make A is for Otto, since we already have a lot of C's. C is the cup. G is the ground. And let's think about what we know. We know that the acceleration of so this measured acceleration, what would be the subscripts for that? Cup relative to, C relative to Otto, yeah. So this is C relative to A, and that is 15, negative 9.81. We're going to use the same thing that we did before. We know that really what happens when something falls is that in the ground frame, its acceleration is down at 9.81. So the acceleration of the cup relative to the ground is 0, negative 9.81. And what we want to find, well, what is it that we want to find? The acceleration of, we want to find the acceleration of the car, the Otto, relative to the ground. Okay, so I'm going to do it. So last time I did it by just putting them in whatever order I wanted and then finding negatives. This is the way I tend to do it. I'm just gonna put these three in an order that works, and then I'll rearrange it to solve for what I want. So this is kind of the other way to think about it. So I'm going to say the acceleration of the cup relative to the ground is equal to the acceleration cup relative to the ground is the acceleration of the cup relative to A plus the acceleration of A relative to the ground. And then fill in what you know and solve. So 15, negative 9.81 is equal to, nope, that's the wrong one, sorry. Cup relative to the ground is 0, negative 9.81. And that's equal to 15, negative 9.81, plus the acceleration of A relative to G. And now just do that subtraction, and you get that acceleration of A relative to G is equal to 0, negative 9.81, minus 15, negative 9.81. And that is negative 15, 0. So it looks to you like the cup accelerates forward. What's really happening is the car is accelerating backwards. Question?
What was your reason for starting with the cup relative to the ground?
I just put, because I had these three, these are the three I have. And so I just put them in a form that met that requirement of fraction multiplication. There are two ways you can think of it, and that's one of the two. The other way is to put them in whatever order you want and then just change the signs of them to switch the subscripts so that it satisfies the fraction multiplication. But you will get used to one sort of thing, like if you always set up, so on these problems, there's always there's going to be a ground, okay? And then there's going to be some intermediate vehicle or coordinate system or whatever, and then there's going to be an object. And set the object relative to the ground equal to the sum of the other two. So that's what I did there. You could also use this for okay, so let's say that there's a train goes on in both directions, and someone on the train is running, okay? And these are glass train cars, so you can see through them. Okay. A camera on the ground says the train's velocity is, let's say, 30 meters per second. Okay? I guess make that a comma. And this same camera says that the man's velocity is let's make it 40. Is that too fast? Yes, that's way too fast. Let's make it 35. How fast is the man really running? Okay, so, I mean, this one I think you can probably just do in your head because it's just the difference between those. But to do it with this relative velocities approach, we would say that the velocity of the train relative to the ground is 30, 0. The velocity of the man relative to the ground is 35, 0. And we want to calculate the velocity of the man relative to the train. So I'll set that up as, you know, what I was just saying, John, is I'm going to set that up as velocity of the man relative to the ground, because it's like sort of the final object relative to the ground frame, is equal to the velocity of the final object relative to the intermediate frame or the vehicle, plus the velocity of the intermediate object or vehicle relative to the ground. And so we have crash. I know, so close. So we have that 35, 0 is equal to the velocity of the man relative to the train plus 30, 0. Subtract 30, 0 from both sides, and you get that the velocity of the man relative to the train is equal to 35, 0 minus 30, 0, or 5, 0. This actually happened for me once. I was like, this train was going by with my son on. He's like, Dad, look at me. I'm going, 50 miles an hour. I'm like, no, you're not, you stupid idiot. You're going like 2 miles an hour. You're just on a train. Kids. Okay, any questions about that? All right, that's all. So I'll give you a couple problems on that, and then we'll do circular motion and spherical motion on Friday.